Welcome back to Fundamentals of Machine Learning for Earth Science. This is part 3, where we will be discussing model tuning, parameter optimization, and additional machine learning algorithms. Once again, my name is Brock Blevins, training coordinator for the NASA Applied Remote Sensing Training Program, or ARSET, and I'll be your host for this training. We are at the final part of the training, and just to review, the objectives of this training was to recognize the most common machine learning methods used for processing Earth science data, describe the benefits and limitations, explain how to apply basic machine learning algorithms and techniques to remote sensing data, use an analysis-appropriate training data set to evaluate conditions and solutions for given case studies, and to complete basic procedures to interpret, refine, and evaluate the accuracy of the results of machine learning analysis. Just as a reminder, this is an introductory webinar series. There aren't a lot of prerequisites necessarily coming into today, but if you aren't very familiar with the fundamentals and the concepts and the terminology of remote sensing, we suggest you check out our resource session 1 of our on-demand Fundamentals of Remote Sensing training. Attendees will also need to access Google Drive and Google Colab to work with the code today. To access these resources, users must have an email ending in gmail.com. We'll have the recording of this training available within 48 hours, and so you can go through at your own pace. So here was our journey over the last 3 weeks. We are in part 3, and the homework is now available. This will be due May 19th, and you can find that under part 3 on the training webpage. It is a Google form, and that'll be due May 19th. Throughout this presentation, please feel free to type your questions to the trainers in the questions section. All the questions being asked will be moved to a question and answer document, and we'll go through those at the end of the training. So now I'll pass this off to our trainer, Jordan Caraballo-Vega. Thank you, Jordan.
Okay, so hello everyone. Thank you very much for being back. Today we're discussing part 3, and this session we're gonna concentrate on model tuning, parameter optimization, and then we're gonna introduce additional machine learning algorithms through the session. The outline of this session: first, we're gonna do an overview of model tuning and parameter optimization. We're gonna do an exercise to optimize our existing model that we trained on session 2. We're gonna provide an overview of model explainability and interpretability. And then we're gonna provide an overview of additional machine learning algorithms that you can use for your own science use cases. At the end, we're gonna have a hands-on Google Colab exercise to improve some of the water classification models we were developing on the previous sessions. And then we're gonna have a post assignment in the QA. And just as a reminder, as our previous sessions, all of the materials are available on the GitHub repository. So feel free to jump onto it and follow the session while we discuss. So the training objectives of session 3, we're gonna recognize the most common optimization methods for machine learning algorithms used for processing earth science data. We're gonna describe the benefits and limitations of some of these machine learning algorithms, optimizations for earth science analyses. And then we're gonna explain how to apply basic explainable artificial intelligence techniques for machine learning algorithms in a meaningful manner to remote sensing data. Okay, so let's start with an overview of model tuning optimization. From a summary from session 2, we train a random forest model that would perform binary classification of water and no water pixels using some of the MODIS surface reflectance data. And we provide kind of this basic data set that we would download and train on, and then perform predictions out of it. We also evaluated our model using our test data set, and we perform inference both using a tabular data set, so we already had our features set up, but then also using raster tiles, so geotiff files that we would pre-process and put into tabular format to feed into our random forest model. In general, our model was able to, one, successfully identify water pixels, but we were also able to identify locations where the model needs improvement. And these are some of the input bands and some of the feature importance that we were looking at, where our surface reflectance band 2 was actually one of the most important features at the time of improving our model. Now, the training method that we used on our previous exercise was basically doing a cross-validation k-fold optimization. And just to reiterate on the concept is that we take our training data and we split it into k-folds. In our case, we were doing 5 because of time constraint, but then you have several iterations of the same model where you can extract then the best model out of all of the iterations. And one of the things that this buys us is to have a model that can be strong enough or that can be general enough to perform good across all of the training data set that we have and also the test data set. It also helps on the generalization side of things. Now, your first model will not always be the best. Your first model will not always be the most accurate. You might have false positives, false negatives on your first model, and that is okay. The libraries that we have been discussing through this training, they mostly focus on using some of the default parameters from these models. So we need to perform additional steps to find which of these parameters are actually the most useful based on our use case. And most of the machine learning applications, they just provide that. They provide some of these basic default parameters that are useful for many of the applications that they have been testing on. Now, some of our earth science data sets, they're just unique. They are different. They have different spectral responses. We may have a lot of noise. We may have locations where we might have haze from clouds. There are just so many nuances and variances on our earth science data sets that we just need to optimize to find the best hyperparameters to work from. And these hyperparameters, they are just set before the learning process begins, and they would actually influence the model convergence. If you have a bad number or an incorrect number of hyperparameters set for a particular iteration of training, you might never reach convergence, or your model might never learn the features that you bring into it. And just to add the random forest as an example, if our number of trees is too low, we might simply overfit because our model hasn't reached a way of generalizing across unseen samples, or samples that are not representative from what you have been splitting your random forest on. Another option, and this is what we're going to be discussing, is how can we improve these hyperparameters without having to manually go through all of these steps? How can we improve this step as it's part of our development workflow without having to have any external knowledge, besides at least knowing the basics? On the right-hand side, we have some of the actual hyperparameters from the random forest. This is just an example of how hyperparameters would look like in regards to a specific algorithm. In this case, is an XGBoost algorithm where we have learning rate, max depth, the max number of leaf nodes, and then L2 regularization that we use to avoid overfitting. In the case of our random forest model, instead of having a learning rate and an L2 regularization, our hyperparameters might only be like the max depth, the max number of nodes, and then the max number of leaf nodes. Let's continue then with the model tuning. Most of the time, we're not optimizing our models just for those common features. We're actually trying to optimize our model to improve so we can generalize across uncommon features. Most of the times on your first training iteration, you're going to get most of the easy tasks or most of the similar tasks to be predicted properly. Now, those outliers or those regions that are not completely similar to your representative training data set, they might need additional help. And this is where model tuning and parameterization comes into play. So by fine-tuning our model, we can then maximize our performance to get the highest rate of performance possible. And here we define performance as kind of the highest rate possible, but there are many ways of measuring performance. We can see performance as, let's say, the most accurate model, but we can also try to see performance as, let's say, the model with less false positives, or the model with less false negatives. we can define that optimization rule on our end based on our application. Sometimes we just want the model to be generalized enough to have a good accuracy. But sometimes we want our models to concentrate more on those hard sample or on those small features that might not be represented on the training data. Finally, from the model tuning, this is just an experimental process. And the idea is to find those optimal values for those hyperparameters to then maximize our performance. But we are not going to get there on the first try because there are many ways of tuning these models. And on the right-hand side, we're just kind of showing how the workflow looks like. We have several testing or several experiments where we change some of the values from our hyperparameters. And in this case, we're actually changing the number of layers for a neural network and then the number of neurons for that particular neural network, including the learning rate. By having multiple experiments of this, we can actually monitor how the performance of our neural network is going through and how that is affecting the actual performance of the model. Know that by the end of these 3 iterations, the model with the highest accuracy was the one with 5 layers, and then 256 neurons. Not necessarily the one with the most or highest number of neurons, but the one with the highest number of layers. So some of the techniques for modeling are, first of all, having a robust evaluation criterion that we need to identify before starting to model or to tune our algorithm. And the idea behind this is that we need to make sure that we know how we want to approach our optimization. We want to know what we want to improve from our model performance related to our training data set, and in this case, our test data set. We have 2 methods. We have the manual model tuning, and the idea of manual model tuning is that we're going to basically use our intuition. We're going to use our knowledge on the algorithm to improve it, to build upon it. And sometimes, once you kind of familiarize yourself with some of these algorithms, you know where things are wrong. You know that your model might be overfitting because you just have a small number of trees. And manual model tuning only comes by experience and by knowing the mechanics and the rules behind each one of the models. Now, if we do not have some of that background knowledge, sometimes we can then proceed to use automated model tuning. And this model tuning, while it is automated, you still need to have at least some background knowledge to know which parameters should you use or which experiments you should design. But you don't need to actually go and manually change some of these parameters by default. Another positive thing about automated model tuning is that instead of having to guess, you can just create a n number of tests that would just iterate above all of the experiments that you said, which in this case would allow you to do faster optimization of the model without having to spend n number of times in the iterations and just thinking about what would work. On the right-hand side, we have a diagram of some of the parameter tuning methods or steps. First of all, we kind of start our hyperparameter tuning step, and then we apply a search method, which in this case we have 3. We have a grid method, we have a random method, and we have a Bayesian method for one of the hyperparameter sets. The idea is that we're going to iterate over each one of these methods by doing cross-validation, splitting the data into k-folds like we did on our previous experiment. And then for each one of those k-folds, we're going to then calculate the score of accuracy that we want, any average accuracy from all of the models, and then assign that value to the iteration that we just experimented with. Assuming we do all of the grid experiments or even the random search, we end up having the number of models with the best performance that we can then select from for further testing. Okay, so a bit of more details just to kind of make sure that we explain this properly. So on the grid search method, the user is the one that defines a set of values for each hyperparameter to form a grid. So the user has some knowledge on what hyperparameters to choose from to then perform the experiments. And this can be different combinations of parameters. We can try different values. We can try different values based on literature or even on the actual knowledge that you might have or background about the algorithm. We also have the random search. And in the random search, the algorithm would try random combinations of these hyperparameters to try every single possible combination. And note that this can be computing intensive because of the n number of experiments that we have, but you can limit the number of experiments or the range of these hyperparameters to avoid some of the additional computational burden. The last step that we're going to discuss here is the Bayesian search, which in this case keeps track of the past evaluation of results to inform the new experiments that you're going to be selecting or that you're going to be creating. So in this case, we're kind of using past information from, let's say, a previous experiment to then improve upon the actual score of the next experiment that we have. And this one as well is kind of computer intensive because you're kind of saving the data from both previous and post experiment, but then you're finding the surrogate of the hyperparameters that are going to give you the best performance in an automated way, where you don't need to think about some of the parameters that might be running through the optimization. And by the end, what you have is a combination of hyperparameters that would just yield the best result based on whatever criterion you chose. Okay, so now let's go to our first exercise of session 3. We're going to tune and optimize our random forest model. Okay, so similar to our previous sessions, we're going to go to our GitHub repository where we have all the material for this training, and we're going to look for materials for training in session number 3, which in this case is model tuning. And I click on the Colab logo, and then we can start rolling. In this notebook, we're going to first familiarize ourselves with optimization techniques for machine learning. We're going to introduce some of the basics for this random forest model, but these are applicable across the board. In this work, we're going to keep using the same modest data set that we have been using across the training, and then we're going to apply the workflow to kind of improve our model, or at least prove the concept of model tuning across the board. First, we import some of our libraries. We need to download some of our source code and install some of the dependencies that we might not have. And just to reiterate on this, you can use Google Colab for free, but some packages might be missing. So you can just go ahead and install them on your session by having the exclamation point in front. Once we have that, we can just go ahead and import some of the libraries that we're going to be working with. Note that in this particular notebook, we're going to be using Optuna to do some of the parameter optimization techniques. So once we have that, we can define our general variables. Note that we still are using the same feature importance bands that we got from the exploratory data analysis exercise. And then we're then using some of these to then download our data. So in this step, we just download some of the training data we have, and then we split it into our trained data set and then our test data set. We then perform the split between our X features, our column features, and then our target or label, which in this case are water and not water pixels. This is just to make sure that we are having the features that we want, that we don't have any extra features that we might be having. This is always a good practice to make sure that you monitor whatever is going into your model. And then just doing some additional exploratory data analysis to make sure that none of our values are out of order, that we don't find any metrics that we're not looking for. And this is really important because you need to know at least your data. You need to know the physical parameters of your data to then understand how your model is going to perform and how you might be able to optimize the model. Because in this exercise, we're actually tuning the model. But in general, once you reach a plateau of how much you can tune your model, you might need to then look at how your data set is built and what features you might need to improve the performance of your model. And here we're just looking at some of the actual metrics or outliers from our data set. We're looking that none of them are higher than 10,000, but if we actually go a bit lower, we can see any other outliers that might be coming through. Here, we're gonna define how we're gonna search for the optimization hyperparameters. The first step is to set trees only, because we only want to tune, let's say, the number of estimators, the max step, the max sample split, and the minimals of samples per live. And all of these parameters are really important on the performance of the random forest because they control the structure of the resulting trees from training. And if we wanted to train on every single or optimize on every single parameter from the random forest, we would need to then just include all of them, and computationally it would be expensive. So give it a try. If you select that you want to optimize on every single one, you can just set the parameter to false, and then you can just go from there. Once we understand which parameters we want to test, we can then proceed to define which objective function we want to iterate over to then see and monitor the performance of our models. We can do this manually as well as using expert knowledge about the algorithm. So for example, increasing the number of estimators, if the model is overfitting, would probably improve the performance of our random forest. Now, some other algorithms like neural networks or even XGBoost algorithms, they might not be as sensitive as a random forest to some of these parameters. They might be more resilient in regards to being able to overcome some of these hyperparameter optimization exercises. So in the next cell here, we kind of define several number of trees, depths to test, and then other parameters that we want to test from the architecture of the random forest. And note that we also define some of our metrics, which in this case are going to be precision, the F1 score, which again is the harmonic mean between the precision and the recall, and then the rate of the false positives. Note that we are setting up some of the actual hyperparameters in this section by making some that are going to be static, but then making some that are going to be just trial and error. For example, the number of estimators or the number of trees in this case. If we wanted to test all of the parameters all together, we would then provide a trial for all of the parameters or all of the options of the random forest model. And again, we're doing this basically for the random forest, but you can always choose some of these parameters from whatever architecture you're using to then perform the experiments and iterations on them. Once we have the parameters set that we want to test on, we can define our model and then feed over our training data and then perform some predictions out of it. So let's just then start our hyperparameter tuning trials. We first use Optuna login just to make sure that we're going to log every single one of the experiments. And then we're going to create a study based on what are the parameters that we want to test on. And what we're going to do is that we're going to have 25 trials, and then we're going to have our objective function, which in this case, we defined as the list of trees, max depth, min samples, and then the actual min sample split. Once that is done, we can proceed to run our optimization and know how we go from trial 0 to trial 24, accounting for all of our experiments. Know how the performance can be on the end of like 0.97 accuracy through 0.98 and so forth. Know how the number of estimators then continues to change on a gridded fashion just to test a couple of those parameters across the board. Now, once we have done our experiments, we need to visualize the experiments. We need to understand how the model tuning performed and what are the benefits that we got from it. So the metrics to use in this case is the F1 score. And what we're going to do is that we're going to run some of the trial scores to get some of the values or some of the estimates based on the number of estimators. So the number of estimators being 75, because of the best performance that we got was a 0.99 of accuracy across the board. In addition to that, we can actually visualize some of the optimization history in regards to the objective value or the actual experiments that we were running. Now that we have a range between what it would be about 99.5 for the like highest results, between like 0.99 for some of the others. And this kind of taking some of those most performant results out of the actual bucket of them. We can also look at the hyperparameter importances. In this case, we only have a single parameter since we were doing the n number of estimators and only testing on the number of trees. In the assignment for session number 3, you're going to be able to then test on additional hyperparameters to then check on which ones provide the most importance when doing this hyperparameter tuning exercise. At the end of the day, we kind of visualize the loss functions that we were estimating on our optimization, and we can look at what were the estimators across all of the experiments that we run, and the number of experiments that we actually run per objective function. Again, the same thing. When training with the trees only, we can actually see what the precision is based on the number of estimators. Note that the precision reaches kind of a plateau when you are in the 400 number of estimators. So by only having a total of 100 or even less than 100, you're doing and reaching higher performance. Now, in some data sets, this can actually mean that you're overfitting your model, that your model is not performing at the rate good enough that it's going to be able to generalize across unseen samples. So you need to make sure that you kind of understand your data and you test your map visually to understand how the values that you're getting from the scores match the output that you're getting on your map. Okay, so once we know what our hyperparameters are going to look like, we then go ahead and use these hyperparameters to train our model, which in total would be using the number of estimators as 75. Using the k-fold strategy, we then go ahead and do the same k-fold training by iterating over a k of 5 and having multiple scores so we can test the generalization of our training data across all of the testing samples and the training samples. Once we have trained, we can see that we have a couple of iterations. We can see the accuracy per iteration. And then at the end of the day, we can then look at some of the average scores and so forth. Once we have trained and tested a model, we can then get some of the metrics that we're looking for. So overall, we're getting an accuracy of 0.98. And then we can just proceed to calculate some of the previous metrics that we did before. For example, just testing the recall, testing some of the values that we have on the test data set. Know that once we continue to look at the feature importance after tuning and different from the first experiment, our surface reflectance band 2 continues to be of high importance, but NDVI actually increased its importance as well. So this means that by tuning our model, we actually provided the parameters enough to have two of these most important features to be kind of to change based on the number of trees we were optimizing. Okay, so we have optimized our model. We have looked at some of the test scores. We can then go ahead and see our maps or visualize our map. So for this, we're gonna load the model that we just saved, and then we're gonna load a raster data set that we can look at to the experiment. And for exercise of session number 3, you're gonna have additional rasters that you will need to look at and then see if the tuning of your model actually improve the performance across all of the rasters that you're gonna have the exercise for. So in this case, we read a raster. We again do additional feature engineering to calculate some of the indices that we need to complement our raster. And then we go from the array dataset to a tabular format. Once we have the dataset on a tabular format, we can feed that directly into our random forest model and then calculate both the classification output and then the probability output. So at the end of the day, what we end up with is a single band raster that then has the output of our model once it has been optimized through the iteration set. And all of these cells are basically what we discussed in session 2, but are the main way of getting some of those post-processing and QA pixels to be removed out of our final product and to make sure that we clean our final output for better visualization and for better science. Finally, we can go and then visualize through an interactive map using volume the performance of our model. And we can see how we're actually very well predicting some of the characteristics of like power in here and some of the other water bodies that we have around the area. Same with some of the water bodies that we can find in some of these other locations if we turn on and off some of these features. We do still have some of these false positives that can appear in the map, and this could be due to the small data set that we have been using to test across board. So as closing thoughts, we have again downloaded MODIS data. We have performed a graded automatic parameter optimization using techniques for model tuning. These techniques can be used across the board in other parameters, so they provide kind of the fundamentals to tune and automatically improve some of other models. We have trained and performed inference using the hyperparameters that we found to be the most accurate for this particular model and data set. And then we have created additional interactive visualization to look at our maps. Finally, we looked at some of the model explainability aspects, and we found out some of the characteristics that change when we finally optimize our model with the automatic generation of hyperparameter tuning. Next, we're going to have Caleb explaining some of the model explainability and interpretability techniques we can use across the board on some of these models.
Now that Jordan has showed us how to tune a model and get a good model going, let's look at how we can explain some of the results and how we can make an interpretable model. So model explainability and interpretability, all a part of being under the umbrella of XAI, which is Explainable Artificial Intelligence. That's kind of the idea of making models that are able to explain the predictions that they made. As we come to rely on these inferences given by machine learning models in different sectors, it is important that these models be accurate and interpretable. These models need to be able to explain why they made the decisions that they did, and they also need to be accurate. Now, looking off to the right, we can kind of see a graph that shows model accuracy versus model interpretability. It's pretty difficult to get into that sweet spot of having a very accurate model and it being very interpretable. Decision trees and linear logistic regressions are two examples of models that are very interpretable. We can look at their decision-making process and be able to understand the reasoning, but they're not as accurate as something that's a more black box model, such as deep learning, a neural network, or ensembles, to give a few examples. What I mean by black box is that we can't really tell what is going on when we give the model a prediction, and it can't explain the predictions that it made or the reasoning that it used to make those predictions. So accuracy may not be enough. We want to have a machine learning model that is reliable. An unreliable black box model, they're prone to making inconsistent and unpredictable decisions, and they're unable to provide any insight or explanations for these decisions. Model accuracy and model interpretability can sometimes be in conflict with one another. Interpretability is where we can explain why a certain outcome was predicted. And in general, more accurate models tend to be less interpretable. This trade-off between accuracy and robustness rises because the most accurate models are often the most complex, the black box models, and therefore the most difficult to explain. We also want to have a robust model where inputs can be noisy. You know, we have a model that is trained off of surface reflectance data. That can sometimes be noisy. There can be variance in that data, and we still want the model to return accurate results. One kind of big area of explainable AI is the post hoc explainability approach. Post hoc is done after the model is trained. These approaches are methods that are used to explain the predictions made by a machine learning model after it has been trained. These approaches provide insights into how the model arrived at its predictions and can help improve the transparency and interpretability of the model. We'll kind of discuss some post hoc explainability approaches that can be used to explain the predictions made by a machine learning model. Off to the right, we see a list of some approaches. Some are feature relevance, where that involves identifying the most important features that contribute to the output of a machine learning model after it has been trained. That approach can provide insights into how the model arrived at its predictions and help improve the interpretability and transparency of the model. We can also do other methods such as local explanations. If we were to change some of the inputs, how would that affect the outputs? And we can kind of learn and get some explanations of the model's decision-making process based off of those tests. Other methods are some like test explanations, where we can kind of determine the model makes a prediction Y only if some part of the input is above or below a certain threshold. And we can also look at other methods such as model simplification, where we can take a very complex model and reduce those kind of decisions down to a little more simple model that's more easily interpretable. One commonly used tool is SHAP. It's a Python package, and it uses the idea of Shapley additive explanations. Basically, it's a game theory algorithm that's used to determine which features have the most impact on a prediction. It's a model agnostic approach, which means that it doesn't matter what model you're using. It just kind of looks at the input and the output. So it could be a very black box model like a neural network, and it can still work for it. And this SHAP tool can calculate an additive feature importance score for each prediction. And like I said before, that kind of means it can calculate which features contributed the most to raising or lowering, maybe like predicted class probability, say for water. And that's a part of the local explanation sector of post hoc explainability. They're really good for explaining single decisions from these black box models. Down in the bottom right, we see an example of a row from our MODIS training data set. And below that, given our classifier, we can get the SHAP explainability plot, and that tells us which features kind of prompted the class probability output to be higher or lower. We can see that band 6 and band 2 made the prediction go much higher towards a water value. And then NDVI and surface reflectance band 4 tried to push it down towards the land value, but it ended up being 58% probability of water. So we'll call that water. Another example of model explainability with a machine learning algorithm is attention maps with visual transformers. Transformers are a type of use of neural networks where they use a mechanism called an attention mechanism, which basically allows the model to focus on certain areas and certain features in the input and make predictions from that. One really useful thing that comes out of that are these attention maps, basically the maps from the inputs that show where the model is paying attention. And that can kind of tell us where the model is paying attention to and what features are kind of more important in leading to the prediction that it made. It highlights the important regions for the image for that target class. These can lead to a better understanding of how the model is processing the input and which features are most important to the prediction. And next, we will take a look at some of these concepts in practice in a notebook on Google Collaboratory. All right, now we will look at the notebook. It is located, the link for it is located here in the NASA ARSET Machine Learning Fundamentals repository. You can go down to this link right here and open it in Google Collaboratory. We're first going to get rid of all of the outputs that we've already seen and start from scratch. So we've briefly mentioned some topics in machine learning explainability. This is kind of an introductory notebook to familiarize yourself with explainability techniques for machine learning. For this, we'll use data from the MODIS instrument to test several techniques in machine learning algorithms, and we're going to look at different methods of explainable AI. The intent is to introduce this topic of explainability and describe some of the methods. This entire work is done using Python, and it's based on the data set that we've seen before that that is the MODIS toy data set. This is completely normal. We've written this, so it's okay to run anyway. Here we're just going to install some explainability libraries called SHAP and Lime. We'll get into that a little bit later. We've already kind of explained some of SHAP. So we can see that it's installed some of these packages that are necessary that don't come stock with the Google Colab runtime. And now we've also downloaded a pre-trained random forest model. We've pre-trained a model before in the previous notebooks, and here's one that we have located in the repository that we can download anyway, so we can save time on not having to train again. We're going to import the rest of the notebooks that we need. And we're going to init the JavaScript. This is just so we can see some really pretty outputs from the SHAP library. We have some variables that we're going to need, and right here we're going to actually load this path. This is the model that we've downloaded, and we're just going to load it up with joblib, and it is now our random forest model. We're going to download some of the TIFFs that we're going to use to predict on with this random forest model. This is a function that just reads in those TIFFs and then converts them to a NumPy array that we then convert into a data frame that's a tabular data frame that we're familiar with now. And it looks like this. So we see here, we have a lot of points. We have all of the bands that we need, surface reflectance bands 1 through 7, the normalized differentiable vegetation index, and NDWI 1 and 2. Here we're going to define a function that takes that data frame and applies the random forest model to it. So this might take a little bit of time to predict just because it's a lot of data points. So now the random forest has predicted on that data frame. What we're actually going to do is we're going to, we have the predictions from that, and that's water or not water, and we're going to assign that to the data frame that we see here. That is our predictive data frame. We can see that in practice here, where just this last column is that predicted value. So before we get to the model explanation part, let's find some data that is interesting that we could use for some individual prediction explanations. This is data that might be outlier data or some other interesting data that you might want to take a closer look at. Here we have some pixels where the model labeled it water, but the NDVI was very high. So that could be interesting to us. We do this function that kind of sets a threshold, and here we set the threshold for 10,000. And here we see a sample of the data frame that shows rows where the NDVI is above 10,000, and the random forest model labeled it water. The same thing again, it's just making sure that we have the water ones. So we briefly talked about Shapley values and SHAP, and this is kind of a in practice sort of explanation. So the library is in Python. It's a popular and widely used tool that provides a solution to the explainable AI problem. It offers a pretty intuitive way to explain the output of machine learning models by assigning the values to each feature and indicating its contribution to the prediction for a specific instance. So like I said, the SHAP library implements that sort of theory from the Shapley values. And here we're going to use what's called the tree explainer, which works really well with tree-based methods such as random forests, XGBoost, light GBM, or histogram gradient boosted machines. There is an explainer that works for any machine learning algorithm, and that's called the kernel explainer. Here we have some additional resources you can take a look at that kind of go more in depth into the theory of Shapley values and more in practice, along with some tutorials. So here we have the tree explainer. We give it the classifier, which is our random forest, and we also give it the raster data frame, which is the pandas data frame made from the rasters we brought in. We're going to drop the values of water, the predicted values from that predicted high NDVI sample that we took. And here we're just going to get the SHAP values from that. All we need to do is give it that the data frame or the values that we want it to predict on. So one method of explainability is the variable importance plot. And this is all according to the mean SHAP values for each features. And a variable importance plot is important when looking at the explanations a little more globally. We want to see which features are more important according to the SHAP values and have a bigger impact on the model's decision-making process. Here we see surface reflection band 2 and surface reflectance band 5 being pretty important, although band 2 really stands out against the others. We do this with SHAP, that just gives us the summary plot. So here we're going to look at some local interpretation. One really useful aspect of SHAP is the benefit of local interpretability, meaning that it explains the predictions of machine learning models at the individual observation level. This is in contrast to traditional variable importance methods that only provide results for the overall population. With SHAP, we can understand why a particular prediction was made for a specific case and how each predictor contributed to that prediction. This level of transparency allows us to pinpoint and contrast the impacts of different factors on each individual case, and it provides valuable insights into the model's decision-making process. With all that being said, we've defined a function up here that kind of wraps the SHAP force plot, and that's the function that gives us this nice little visual right here. So what we do is we want to look at the first row in our high NDVI setting, and what it gives us is this sort of visual. That's what's called a force plot. And what it gives us is the model probability that it is water, and here we see it's 0.77, so pretty confident that it's water. And we see which features are pushing that prediction towards water and which features are pushing it down towards not water. So we see all of the surface reflectance bands and the calculated indices NDWI 1 and 2 are pushing this up towards our prediction of water. The only thing that's pushing it down just by a little bit is that really high NDVI value. So we don't, according to this, maybe don't have to worry that much about NDVI being really high because all of the other features might make up for it. So let's double check that with a few more examples. This is another example. We see it's just another row in our sample data frame. We see it's, again, pretty confident. 0.68 is our predicted probability. And like we saw before, we see that the rest of the surface reflectance bands and calculated indices besides NDVI push up the probability towards water rather than not water, and NDVI is the only thing pushing it down, but it's not enough to push it towards anything less than 0.5, where it might be, the model might be unsure and push towards not water. Just to triple check, let's look at one more example. We can kind of just see again, it's the same deal with that we saw before. So that's good. We can look at this and we can say, okay, there are instances where NDVI might be high, but the rest of the indicators show that the model is pretty confident in its prediction of water. So that's SHAP. Another explainability tool is called LIME. So that's the Local Interpretable Model Agnostic Explanations package. And what LIME does is LIME creates a very simple and interpretable model from a given model, a random forest, for example. And it only does this for a local area around a given point. It doesn't really give us a global explanation like parts of SHAP can do. What it does is it creates a simple model for only areas in our feature space where we want to take a closer look. So it's a linear approximation of the model's behavior. While this model, this random forest, might be very complex globally, and that means, by globally, I mean in the entire valid feature space, it's easier for LIME to approximate the model around a point of interest. This graph is a really good example. The soft blue and red back here represent the global decision boundaries. However, in the local space, we see here this red cross. This is an area we kind of want to take a look at. And what LIME does is it approximates the decision space, you know, between red and blue here with that simple linear boundary. This works to explain only the area around this point of interest, these other red crosses and blue crosses. And this really approximates the model well in this local area, but it doesn't represent the global decision function as we see. If we were to take this and apply it to everything else, we'd see that it would not fit with what the model's actually doing in other areas of the feature space. These are some additional resources that you can take a look at that probably better explains it than I can, and it also gives us some examples and tutorials to take a further look at this. So in practice, we can import the LIME library, and what we take is the LIME tabular that works for tabular data, and we create a LIME tabular explainer. We give it the data frame to predict, which is our raster data frame. We tell it this is a classification problem. We give it some feature names, and we give it the class names, not water and water. This gives us an object called a LIME explainer. And what we can do is use that further down here. One thing we do need to define before that is a lambda function that's basically given an input, it returns the model probability of the input being water. And we want to return that probability, we want to make sure that that's a float, meaning that it'll give us decimals. So there's a lot going on here in this part. What we have here is we have the LIME explainer and we call explain instance, and we just give it the first row values and we tell it we have 10 features. So first we see that the row we are explaining is on the right side. These are the actual values in this column. So we see we have all of our surface reflectance bands and the calculated indices. This is what's going into the model. On the left, we see the class probabilities. We see high probability of water and less high probability of land, 0.77 to 0.22. And in the middle is what is really interesting. So this is the feature contributions to what pushed this model towards predicting it water. And this is our kind of linear approximation. We see that surface reflectance 5 being in between 94 and less than 297 pushes that towards water, as well as NDWI. Other aspects push it towards not water, but not as much as our feature contributions of surface reflectance 5, NDWI, and some other ones. So this is interesting. Let's take another look at another example. It's the same deal. We have the columns off to the left that are our actual values that is going in. These are our high NDVI samples. We see model probabilities, and in the center, we see the explanation of why this model is predicting water. We can take a closer look at that, where it actually gives us the decision boundaries and the model and the impact that those boundaries have on the model prediction. So this is really nice to look at, because we can see that if the surface reflectance is greater than 297 and less than 1,711 or equal to, that pushes the model maybe a little bit towards not water. So we have another example here, and I'm not going to go into too much more detail just because it's what we've been seeing before. It's just an example of the high NDVI and the model labeling it water. So some closing thoughts. What have we done in this notebook? Well, we've loaded a saved random forest model from disk, and we were able to load a raster in for the model to predict on. And we also used SHAP to visualize feature importances as well as local explanations. And of course, we've also used LIME to calculate and visualize local interpretations of model outputs. So yeah, thank you.
Okay, thank you very much, Caleb. Now we're going to go into our last exercise of session 3, where we're going to introduce the concept of auto machine learning, and then we're going to discuss some of the closing remarks. For this exercise, we're going to head out to our GitHub page, and now we're going to click on the Modis AutoML notebook. Once you click on it, you're going to receive this prompt. And the main idea of this notebook is that we're going to introduce some of the AutoML or auto machine learning features within our data set. And we're going to introduce some of the benefits of using it, and then some of the actual future concepts that you might be able to investigate on your own once we finish this tutorial. As we have done before, we're going to install some of our dependencies. Note that in this case, we're going to install the auto scikit-learn package from Python, which is going to provide some of those auto machine learning features that we're going to need to discuss in this project. Once we have installed the package, we can proceed to import the library. And in our case, we're doing a classification problem. But if you had a regression problem, then you would include the auto scikit-learn plus the regression portion of the library. We go ahead and define some of the default variables that we have been doing so far, create some of the output directories to save some of our images, and then load our training and test data set so we can look at some of the auto machine learning features. Know that one of the important things that we have done through all of our sessions is to create our X and Y variables for training and testing, which we're going to use then for further development on our exercise. The first portion of the exercise is just going to kind of replicate the training mechanisms that we used on our session 2 training loop. And in here, what we do is that we defined a k-fold object where we're going to do k iterations over our data set to decrease the variance between the models that we're going to train with our random forest. And just to kind of do a brief overview of what we did on session 2 is that by using k-fold mechanisms, we reduce the variance of our models, but we also increase the probabilities of generalization because our model is seeing several views of our training data set. Once we define our k-fold approach, we can then define some of the hyperparameters that we need. And we also did some testing on this on session 2 and part of session 3, where we could actually optimize and fine-tune some of these parameters on the fly using automation of the optimizer hyperparameters. Now, this is going to be helpful, let's say, in some exercises where you don't want to optimize your model by your own, but you can also use some of these techniques once you have the, let's say, proper domain knowledge to then optimize the model on your own based on the actual expertise that you have been gaining from these sessions and then further reading that you might do along the line of other projects that you might have. So once we define our model and our classifier, we can proceed to train and do k iterations based on the number of views of our data set that we're going to have. So from these, we're going to probably just average some of the scores that we have from the models that we trained, generate some of the metrics for each one of those models, but then we can actually select both the best accuracy model, but also the average from all of the models that were trained. Now, know that we had to go through all of this iteration process just to train several of these models. Now, when we introduce the concept of auto machine learning, what this library does is that they try to automate every single point of the optimization of your model and model selection pieces. So this particular library, which is called Auto Scikit-learn, allows you to, one, test several models that are available through the library, two, to actually do the hyperparameter optimization on the fly, and then three, to create ensembles of these models. So now we're not training a single random forest model, which is a decision tree ensemble by itself. We're having ensembles of different models that can include random forests, other decision trees, and so forth, that are going to allow us for better generalization across the board. So to define our auto machine learning pipeline, what we do is that we define this auto scikit-learn classifier pipeline, and know how we are not defining any of the hyperparameters of our models. The only things that we're defining is how much time to spend per task, and then how long to run the entire process. And these two steps are important because based on whatever computational resources you have available, you can run this for a shorter amount of time, which would allow you to have just a couple of iterations of models, or for a longer amount of time where you can test more models, more ensembles, and then further optimize the hyperparameters of each one of your models. Once we define our auto machine learning object, we can proceed then to feed our model. And know that we're using the same feed function that we were using on our default K4 iteration from scikit-learn, but now we can then proceed to do some of the predictions. You know that we're getting an overall accuracy of 0.99. Now, we do not know what this auto machine learning algorithm did. And part of the explainability needs that we have for many of these projects is to know what the machine learning is doing and what the model is actually providing based on the input that we give it. So we can investigate some of these auto machine learning features by just looking at some of the objects within it. So the first one is we're going to investigate the performance over time. So we can see how the performance over time increased while the model was training and doing the optimization of several hyperparameters. Okay, so here we can investigate the models that our auto machine learning features we're investigating, and know how we have several models, for example, a multi-layer perceptron classifier, which is basically a neural network, a very simple one, a histogram gradient boosted classifier, a passive aggressive classifier, and so forth. So we have several models that our auto machine learning pipeline was trying and was actually creating ensembles of them to improve our classification performance. Note how we have the ensemble weight, which is going to mean how much weight each one of those models end up being on our final model stack, or on our final ensemble. The higher these weights are, is the higher that model is going to provide input into the final prediction. So we can continue looking at some of the metrics from some of these models. We can actually see some of the cost of these models, like how much did it cost computationally to train these models, but also to perform some of the predictions and testing. So one more thing that we can look at is the leaderboard. So what were the models with the best performance across the board within this ensemble? And we can look at some of the highest performance ones were the random forest, additional decision trees elements, but also we had some gradient boosting algorithms that would provide some input on the final ensemble. The final ensemble weight, we can see that the model with the highest weight is the SGD, which is the highest performing model within our data. Now, it's actually one of the least computationally expensive one that you can just compare with others like the multi-layer perceptron and so forth. So this is just kind of a way of understanding what this auto machine learning features are doing and how the models are being assembled. In order to compare the performance of our k-fold iterations and our auto machine learning one, we can select the best model from the k-folding iterations, but we can then select the auto machine learning ensemble that we just trained on. To do some of the qualitative observations, we can just load some of the rasters we were looking at and then create the rasters data set into tabular formats so we can predict using these models now. Now that we're following the same process that we did in previous notebooks, where we create our tabular data set, and then we have our function then to do the prediction. Now, know that how I changed this function now to include the model that I want to do, so we can do predictions with different models. One of the downsides of this is that the initial raster prediction using a single random forest would probably take about a minute or two to finish. Now, right now we're using an ensemble of many of these models, so the final prediction takes about 27 minutes to finish for a single observation. So this is actually a downside of using an auto machine learning method that has an ensemble of large amounts of model, because now your performance is limited. And you might be able to increase the accuracy of your predictions, but then if performance was a need for your particular project, then you need to kind of consider how this would affect your pipeline. Once we have created our data sets in tabular format, we can just reshape them after prediction, and then we can start doing some post-processing to visualize some of this. Once we plot our QA mask, and we know that we have been filtering some of those bad quality observations, we can then proceed to save our raster and then visualize it interactively, just to kind of have an idea of how these models are performing. In here we have that our green mask is going to be our auto machine learning output, and then our red mask is going to be our single random forest k-fold iteration output. Now that if we do a close up to the actual like power observations, we can then compare how visually some of these models are performing. And know that in some cases, the actual random forest that was trained using the k-fold is actually better in some locations at predicting some of those boundaries of the Lake Powell observations. We could find other locations where the actual ensemble of models from the auto machine learning process are better than the k-fold iteration, but we can just kind of keep comparing the output between them. In regards to the actual numerical and quantitative performance, we saw that both models has a 99% of accuracy, which leads us to, we probably want to increase the number of tiles that we're going to be looking at, just to know how generalized both models are across a larger data set. And for that, we do have an assignment where we are looking at, instead of only Lake Powell, we're looking at other locations where we compare the performance of our auto machine learning method compared to the k-fold iterations of a single random forest. So just as some closing remarks from this exercise, we train a model using k-fold iterations for cross-validation, but also the auto machine learning features from the auto scikit-learn library. We have seen that both are very similar qualitatively and quantitatively, but we should then do additional comparisons across a wider study area and using, let's say, more observations, just to see how much those models generalize across the board. Last but not least, it's really important to mention that while auto machine learning is a really nice step towards automating some of these steps, having the domain knowledge to understand what is happening on the background is a great way of understanding some of the behaviors from the data set that we have in hand. The auto machine learning provides, let's say, an ensemble of many of these models that have been trained and optimized on the fly, but this doesn't necessarily say that the auto machine learning model is going to be better than, let's say, the model that was trained based on domain knowledge, like we have done so far with the random forest. Okay, so we just finished our last exercise. We do have an assignment with a, let's say, broader application at the end of session 3 that you can take a look at, that you can play with, and then you can just modify for your own use case. Now, to kind of provide an overview of what we have been discussing across all of the 3 sessions, we first started by defining what machine learning is and how machine learning can benefit earth science. We also provided examples of how machine learning has been used in earth science and has successfully replaced some of the workflows that we just didn't have in hand with traditional algorithms. Some of these could be land cover. Some of these have been just literally creating products for production outputs that we are using to better understand Earth. So machine learning has proven to be capable of improving some of our workflows, improving some of our, let's say, existing methodologies. And the future of machine learning in earth science is just brilliant, and we have many things to go for in the next couple of years. Now, another thing that we discuss is how the fundamentals of machine learning are basically similar across the board, but most of the time we only change a couple of variables or a couple of algorithms to get some of these jobs done. So by following all of the fundamentals of machine learning that we introduced during the 3 sessions, you will be able to at least understand some of the literature that is online, some of the code that is actually available on GitHub across many of the papers that you're looking at, many of the workflows that are being held into production right now. But that way you can kind of start thinking about your problem in a machine learning way. How can machine learning benefit your project? How can machine learning benefit your science question? And we also discuss how we need to have several questions in hand in order to kind of decide what ideas from machine learning to pursue. How to select the best model is going to depend on that science question that you have, but also the data that you have, the needs from your production pipelines in regards to how fast you need your product, how accurate your model needs to be, how reliant or how resilient your model needs to be in regards to the decision that you're going to make. You're never going to take decisions the same when thinking about a disaster response problem than to whatever a map you're going to be creating for your specific application. So all of those things, you need to keep them in mind in order to make some of these decisions and to select some of the proper techniques that you're going to need for your specific use case. We also introduced some of the concepts of training data generation, how you can think about your training data generation, how you can use unsupervised learning in many cases to create your training data, to save some time at the time of creating that data, and using algorithms that can provide at least a base where you can use your domain knowledge then to improve your training data set. We also provided details on in regards to explainable AI and how some of the time we are able to identify how our machine learning algorithm is thinking, how it's learning from the data we have in hand. Many times we can correlate that with domain knowledge based on our expertise in the science question. And that way we can actually provide input to the actual, let's say, literature that we're writing in regards to how these models are taking decisions, that we know how these black boxes can take decisions upon the problems that we face. This also allows us to understand if we need to add more training data to our model. If we have observations that our model is just not representative enough, that we need to gather data from, then to make our model more generalizable across other applications. Other details that we touched base on was in optimizing our models. The first model that you train is not always going to be the best one that you have across the board. So it's nice to then have this starting point where you just test an initial model, but then you can use automatic fine-tuning and optimization to then have the best model available in hand from whatever hyperparameters you need to optimize. Some of the last closing thoughts is then the use of auto machine learning. You can use some of these software applications then to optimize some of your workflows and to automate some of the decisions that you make during your development process. Now, it's always nice to have in hand that domain knowledge is always going to be important to understand what these machine learning algorithms are doing, even more into auto machine learning features where you do not see from the beginning what the model is thinking or the decisions that the model is pursuing. Some closing thoughts in regards to the actual, let's say, philosophical way of machine learning in earth science. The realm of machine learning is just increasing, and it's just exponentially increasing in the sense of algorithms that are being released, data sets that are being out there, applications of machine learning that sometimes are not even well documented, but the public is just using without even understanding some of the backgrounds of it. So we need to make sure that we do machine learning responsible in the sense of understanding and having that domain knowledge to improve science, not to use machine learning as simply a tool for earth science, but to understand how machine learning is pursuing earth science and how it's actually accelerating many of these workflows. Finally, these sessions were kind of a summary of many of these fundamentals for machine learning. We didn't cover everything, but we provided the tools for you to understand many of the references that are out there that you can then kind of use the basics and the fundamentals from this training to then go on and do additional more complex workflows like convolutional neural networks, like transformers, like many of the foundational machine learning concepts that are out there that are improving some of the workflows that we have. We need to start from a base. We need to start from an informed base. So it's always good to then have those basics and fundamentals in place to then improve the way we do machine learning in earth science. Just to reiterate, we have kind of a homework assignment, and different from the previous sessions. In this one, you're going to have a Google form exam that you're going to need to fill out in order to get the completion certificate from attending this this training session. And it has been a pleasure for us to be part of this training session, so we appreciate your time. We hope that all of these sessions were of use and are going to be of, let's say, great impact to your future in machine learning, and will allow you to at least start not from scratch, but from an informed base to leverage machine learning into your projects and your science questions. So thank you very much for that.
Thank you very much, Jordan. Thank you for taking the time to give us your closing remarks and to summarize the series like that. That was very useful. Here are our contacts. If you have any further questions, you can contact myself or the trainers that you saw in this series over the last 3 weeks. Here is the training web page where you can find all the materials, PowerPoint presentations, the videos, and the homework. And I've also included our primary ARSET website where you can check out other great trainings, as well as follow us on Twitter to find out about more announcements from NASA Earth Sciences. So now we can begin addressing your questions. Please continue to type your questions into the questions box, and we will address them in the order in which they were received. Thank you. Okay, welcome to the question and answer session. We've been receiving many great questions throughout this presentation here today, and we will do our best to make our way through these with the time remaining, and we will post this to the training webpage as soon as we've cleaned it up and for accuracy. Just one clarification, the homework is a Google form found under part 3 on the training webpage. And you just need to turn that in, submit it by the 25th. So there may have been a slide saying that it was due on the 19th, but we extended that for an extra week to the 25th. And these questions refer to the questions at the end of each one of the notebooks in the homework sessions. So let's get started. Question 1. We've generated a feature importance chart using MDI and skitlearn. On the y-axis, it shows mean decrease in impurity running from 0 to 0.06. I'm not sure why these numbers exactly mean. How do I interpret this range?
Yeah, I can take that.
Thank you, Caleb.
Yeah, so generating that mean decrease in impurity, these importances are measured by seeing like how the overall impurity of the model decreases when a feature is used to make a split in a node in a tree. This is really getting into how a random forest works. So You can dive deeper into the links that we've provided, but basically what those numbers mean is it's pretty straightforward. A higher value for the mean decrease in impurity for a specific feature, that means it's more important to the model, or it means the model relied on it more heavily on that when it was used to make predictions.
Great, thank you. And I placed the links that you see on your screen into the chat so you can access them now. Question 2, can you kindly comment on how to tackle biases and discrimination in selection of training of labeled data?
Yeah, this is Mark. I'll take that one. So, I mean, basically, there's some bias in all data, and there's not a whole lot we can automate it all. So, the key thing is to recognize that the biases are there, and there is some impact, and then you just try to explain it in your outputs as best you can. So, yeah, it's just the biases are there. We just have to acknowledge that they're there, and then work with them as best we can.
That's a good caveat. Thank you very much, Mark. Question 3, do you know about using genetic algorithm for model tuning and optimization? Is it sort of a random search? I wasn't familiar with the genetic algorithm. Maybe you are.
Hey, so the techniques we mentioned in this training are both manual and automated techniques. So on the manual techniques, kind of use your own domain knowledge of the algorithm and you change those hyperparameters manually. On the automated side of things, we discussed 3 kind of methods. One is the random one, where you allow the optimization algorithm to just select randomly hyperparameters. The second one was a grid-based one, which requires you to have some domain knowledge and then provide a list of those hyperparameters to use. And then the other one is the Bayesian algorithm, which would allow them to use prior knowledge from the optimization and then improve upon that.
Thank you. Question 4, are the precision recall and F-score interchangeably used as accuracy assessment reports like kappa or producer accuracy? Can you provide any articles related to the parameters used as model evaluators in science of total environments?
Yeah, so this is Jordan again. So each one of these metrics actually look for different characteristics from your output. And the idea is that you're going to use each one of those metrics to target specific behaviors from your model. So precision will give you the accuracy of those positive predictions, but then recall will give you the completeness of those positive predictions. F1 score is basically kind of a in between those two, just to balance them. And then the over accuracy is just kind of the overall performance of the model. We are caring about the classes that are involved or anything else. I also added some references to producer and user accuracy that you can kind of reference, but basically we're just looking at omission and commission error, and those are not given by like the overall kappa or even like over accuracy scores. So they're just kind of different ways of looking or at the interpretability of your model.
Thank you. And once again, I did place those links into the chat, so please navigate there if you want to access those. Question 5, this is great. We have a high school student learning machine learning and data analytics, so that's wonderful. I'm so glad that you found our course. Could you provide some free and maybe not free resources to understand machine learning programming better? And it looks like there are a couple resources here, and I will place these into the chat once again. Please check these out. Thank you for supplying those, guys. Question 6, this seems pretty in the weeds here and definitely getting into the code. I'm trying to find
I can just answer that one real quick.
Yeah, maybe you could address it better than I.
Yeah, so there is a reference to a volume helper module missing. There's a cell on the notebooks where we download that module. So just make sure to press on that cell before proceeding to run all of the other cells from your notebook.
All right, thank you very much for that clarification. Hopefully that helps this person out and any others that ran into the same problem. Question 7. The model should not detect river water lines as outputs as well. those should be considered as water pixels. Is that correct?
So that's mine. This is Mark. So the model is designed to detect water. It doesn't care whether it's ocean, lake, or a river. If it can detect it as water, it's going to label it as water. So if you really wanted to separate those into different classes, you would either need you would probably need to do it as a two-step process, or certainly you would want a different method than random forest to get there. So yeah.
Thank you very much, Mark. Question 8, how do we determine whether the image produced has a false positive or not?
That's me again. So once you produce the output map, so you apply your model to the data to get your prediction. You need to validate the map, and the false positives, false negatives will be identified in that process. You can do that either with a validation data set if you happen to have one, or you can do it through manually through visual interpretation. And obviously that'll get you the answer to whether you have false positives or negatives.
Yeah, thank you. That's a pretty common theme when it comes to Earth observations, especially if you're going to use them in a real world application. Verification and validation will be necessary. Question 9.
Yeah, exactly. That's the result that you get from the model is really just an inference. And then, we still have to interpret that to make sure that it's a valid map as an output. So the validation process lets us go from inference to, an actual valid map on the other side.
Thank you. Question 9, in a robustness model, what do you mean by input can be noisy?
Yeah, that was me. I was referring to how real world data can be noisy, and by noisy I mean there can be errors, inconsistencies, or other things like outliers due to some unnatural factors such as instrument malfunctions, data acquisition errors, processing problems, something like that. We refer to this as noisy because the data has kind of been corrupted or contaminated in some way, and that can definitely make it difficult for the model to make accurate predictions. And we basically want a model to be robust, and by that we mean we want it to be able to still draw meaningful and accurate predictions despite maybe this data being noisy.
Thank you, Caleb. Question 10, do you know if random forest can also generate maps of probability that a cover is found in a specific location instead of regression or classification? And to get a map that goes from 0 to 1, where 1 is a high probability?
Yeah, so the random forest from the scikit-learn module provides a predict proba option, which is going to output the probabilities for that specific feature or pixel that you're going to be classifying on. It's going to be from 0 to 1. So if you use that one to know which probabilities you're going to have for each one of the pixels. In regards to the geographical area, it's just going to depend on the resolution of your data and the features that you're using for training and doing the inference.
Great. Thank you. Question 11 on the assignment. So when running assignment 1 in Google Colab, when running the third cell, getting an error, a session crash for an unknown reason, and still trying to identify what caused a crash. Is there a good place to look to help with this?
Hey, so the first one is to kind of follow the instructions that are above each one of these cells, because some of these cells are going to restart the kernel just to install some of those GPU drivers. So you would probably need to just run these cells one by one, allow the kernel to restart, and then the drivers and dependencies are going to be installed for the GPU job. The other option is you can just download the notebook if you have like a local system that you want to run with GPUs, and just run it locally.
Great. Question 12, can this technique help to predict areas that will have floods and those that are likely to experience drought conditions now and in the future? Is this capable of such things?
Yeah, that's me again. Hold on, I'm scrolling back up to my answer. So yeah, what you could do is use this technique to generate a time series of maps that could be analyzed to determine whether the current conditions are a departure from the normal, whatever normal is for that particular area. And that'll give you some clues as to the onset of drought or flood. But to be sure, you would really want to combine this, your output maps, with other information from the area, like precipitation, possibly soil moisture, and other things, to, if you really wanted to get into the idea of, susceptibility for drought or flood. And that would help you build confidence with your total prediction.
Great, and I can see this being very useful for things like that, and why predicting areas that might flood would be very important for a number of reasons. And it's nice to know that maybe this technique can help with that. I think maybe digital elevation model data sets could also be used to be combined with things like that with precipitation.
Yep, exactly.
Question 3, I may have missed it, but is it possible to use the Optunal library for XGBoost tuning? Is there an example of XGBoost for regression-based model construction and tuning available?
Yeah, it's a great question there. It's certainly possible to use Optuna with XGBoost, and XGBoost is actually a model that can be hyperparameter tuning can greatly affect model performance for XGBoost, so it's really important to do it. I've put some examples from other sources. We don't have example with regression and XGBoost hyperparameter tuning, but those should give you a good idea of how to do it.
Thank you. I placed those into the chat. 14, is it possible to employ SHAP to eliminate some features that impact predictions negatively?
That's me again. It's certainly possible, but it's not necessarily recommended. There's a couple of reasons. One is that looking at those individual explanations doesn't give us an accurate representation of how important a feature is to the overall model performance. While you're looking at a few local explainable predictions and it shows that maybe NDVI is having a negative effect on the prediction, that's only the case for those. It may not be the case for the entire prediction space. Another reason is that you can have correlated features, of course. SHAP considers each feature in isolation without taking into account the correlations between those features, and it's certainly possible that a feature might have a low SHAP value and be unimportant or negatively affect the predictions according to the local explanations, but it it could be correlated with other features.
Great, thank you for that guidance. Question 15, for the explainability part, those SHAP results may be used to eliminate NDVI. Can the SHAP results be used to eliminate NDVI as a feature for the model? Oh, kind of a follow-on.
So yeah, kind of a follow-on for the above one. It's generally not recommended. I'd just like to say, remember in this case, for the specific example we're looking at examples where the NDVI is anomalous in a sense. And it may show that the NDVI has a negative impact due to us looking at these weird sort of cases, but it's not necessarily indicative of overall impact.
Thank you. Question 16, with SHAP local explainability, where it was showing the influence of all the variables, was it looking at individual pixels?
Yep, it was. For those local explanations, it was looking at just single pixels, a single row of data.
Great, thank you very much. Hopefully that clears it up. Okay, question 17. NDVI values greater than 1,000 due to atmospheric correction. Is it possible that the high NDVI values represent some vegetation within the areas classified as water?
Right, that one's mine. So NDVI greater than 1 can happen if both the red and the NIR values are very, very low. So imagine a red value that's say 3 and an NIR value that's like 8, that's going to result in a very high NDVI value just because of the math. So, this can result in anomalous calculations of NDVI. And this can happen whether you're using a top of atmosphere data set or a surface reflectance. And the values don't happen all that frequently, but they do need to be captured in your algorithm to avoid unusual results in your output maps.
Thank you, Mark. And I know that we're running over, so we're just going to address this last question 18 here. And we'll do our best to get to the rest and get this posted. But in the meantime, question 18. In the example of model tuning, the range of precisions generated by different hyperparameterizations was very small. It didn't seem to be making a very big difference to the precision. In your experience, maybe with more complex classifications, how much difference in model performance can we expect by tuning parameters?
Yeah, so influence of hyperparameters can kind of be attributed to both kind of the data set that you're working with and the models that you're using. In the case that we're showing, we have small amounts of data, and the classification task is relatively simple according to the models. It's able to pick up on a relatively accurate decision boundary for this water not water problem. So changing up the hyperparameters a lot doesn't really seem to affect the performance. It can of course improve it marginally, but for more complicated problems, hyperparameters can definitely have a greater impact on the model, and opening that range of hyperparameters that you're working with. They can control like stuff like model complexity and the regularization of those models, and that all helps you kind of adapt the model to the complexity of your problem. Stuff like models like random forests actually don't usually need a lot of tuning since they work pretty well out of the box, and they have a small amount of hyperparameters that don't necessarily change the performance that much. Of course, some do. I'll put that caveat in there. Other models such as XGBoost are greatly affected by hyperparameters. That you can really mess with it, and that's a case where you can really tune up your hyperparameters and get much different results, good or bad.
Thank you. So that brings us to the end here today of the series. And I know, Jordan, you had a great summary, great concluding remarks. But I just want to give the other trainers an opportunity to say a little something to the audience here, if you choose. And if not, that's okay. We thank everybody for attending these last 3 weeks. All the recordings are available on the training webpage for you to review and go through at your own pace. Remember, again, the homework is due on the 25th, and if you attended all the trainings and submit the homework, you can receive a certificate of completion within about 3 months. We had a lot of, this was a very popular topic, and given the popularity of this topic and the participation that we saw, I don't know if you all know, but you're one of over 3,000 individuals that took this training over the last 3 weeks from around the globe. So I do believe that we're going to have more machine learning incorporated into different Earth observation application trainings that ARSET puts out in the future. So I hope you enjoyed this, and please reach out to myself if you have any questions. And thank you very much, and I hope you have a great rest of your week.